something we have been working on now since 2015 is finally starting to reach fruition. So this is the American Nuclear Society's working group on developing an MSR design safety standard. PIN's form for this was approved in 2015, and we finally got something into the balloting process in August of this year. That tells you what the speed of the standards development process is, and the fact that it's a consensus product. First of all, what's a design safety standard? This is not a standards group, so we're trying to give you some explanation of why do you have these things and what are they useful for. Well, the standard is designed to increase the safety, adequacy, design, and evaluation efficiency and predictability. Essentially, this gives you a blueprint for what gives you an acceptable level of safety, and that the regulator has said, if you follow this method and you follow it correctly, this gives you an acceptable result. So the existing body of regulations and safety evaluation methods are based upon the characteristics of the existing fleet. Well, the existing fleet in the US is LWRs. So MSRs represent a substantial technological departure from LWRs. So the rules and how do you do things are different. And it's very cumbersome to evaluate the safety of each new MSR design based upon customized exceptions to existing practice. So what we're trying to do is, what exceptions and what things do you have to do that are the same for any MSR? Yes, we recognize that MSRs are a very diverse and very broad class of reactors. However, all LWRs follow a set of rules with some exceptions. I mean, BWRs and PWRs have separate sets of things within there. However, there's an awful lot which is in common on all water-cooled reactors. So we're trying to say, how can we be helpful with efficiency and predictability? So in any case, the safety principles are the same for any nuclear power plant. And this has been recognized from the beginning on developing the regulations. And so the specific wording within regulations says, well, these are the basic principles, extract the principles and apply them to your plant. So an MSR-focused design safety standard preserves and translates the existing safety principles to MSR. Says, what does this mean, in terms of containment for an MSR? What does control mean for an MSR? And then we address some specific MSR issues, because there are some things which are distinctive because this is a molten salt reactor. Draft standard, because these are consensus processes, on there. They're developed by a broad team representing developers, national laboratory staff, universities, and regulators. I apologize that I do not have the full list of people. That actually fills up more pages on here. There are several of the people who have contributed to that who have been who are in this workshop. I will call out a couple of them distinctive because they've made substantial contributions to this, and I apologize if I don't hit you. Let me see. Copenhagen Atomics has been Aslak Stubskard has been very strongly. Vince Latowski, who's Thorium Energy Alliance. Abdullah Jaude from INL has made substantial contributions. Brian Johnson made substantial contributions from TerraPower. But this represents a large body of common effort, and there are others as well. So the working group was organized in 2015. We had an early draft by 2018. We had a hiatus where the NRC developed regulatory guides 1.232 and 1.233, which really represented substantial changes in how do you evaluate the safety of advanced reactors. Development resumed in 2020, and so we've basically been doing 2 hours per week virtual team meetings, and so we're getting a lot of time in the virtual meetings here. An initial draft was submitted for balloting in August 2021. Subcommittee votes and comments, we got those back in early October, and we are now starting the comment resolution process. We got on the order of 20 comments and such, but and comment resolution may take a substantial period of time. We don't know. No, we have not really undergone that, but we're hoping maybe next year we'll have a published standard. The standard is intended to be applicable to both traditional, deterministic, and probabilistic safety adequacy evaluation processes. What we've done is the technical information is organized into 3 main sections. There's a background on MSR safety and accident progression concepts that highlights the differences from LWRs, sort of trying to help the designers and the regulators to think, what do you think about differently on how accidents progress? What are the safety implications of the of MSRs? And then the second, that's actually our section 3, is the MSR specific design criteria, translating the safety requirements of the general design criteria, which is 10 CFR 50 Appendix A criteria, or the advanced reactor design criteria that were provided in Regulatory Guide 1.232 to MSRs. And we augmented these with some additional MSR specific design criteria. And I'll have an example for that in the next couple of slides. And then the next section is a risk-informed design process guidance that describes MSR specific considerations for probabilistic plant safety evaluation. So the background section highlights the shifts in the safety basis relative to LWRs. The section serves as an information resource on issues that need to be considered during the design and evaluation of MSRs. It's not, there aren't any shalls in this in terms of a standard. It's sort of, this is what you need to think about it. Some example content on there is design options enabled by multi-layer radionuclide retention embodied in functional containment, is just sort of how you might do this. The concept of applying specified acceptable radionuclide release design limits, SARDLs, instead of specified acceptable fuel design limits, SAFTLs, which are used in LWRs because SAFTLs are essentially our core damage frequency, and they're a concept that involved, which is a surrogate for accident progression in there, and you just can't really damage the fuel in a liquid fuel system. And this is a similar method that's also being applied to the TRISO-fueled reactors in the solid fuel systems. And then safety issues arising from employing a common intercontainment layer and the potential to leak a large fraction of the radionuclides into the next containment volume as a result of a breach. Essentially, if you poke a hole in the cover gas system while it's working, you can release a very substantial amount of radionuclides into the next layer. That's a potentially big thing. You must design your reactor so that you cannot release all of your cover gases out into the environment. Then the MSR specific design criteria, again, derived from the general design criteria 10 CFR 50 Appendix A. The principal design criteria establish the necessary design, fabrication, construction, testing, and performance requirements for structures, systems, and components that are important to safety. The general design criteria, this is just a quote from Part 50 Appendix A, are also considered to be generally applicable to other types of nuclear power units and are intended to provide guidance in establishing the principal design criteria for other such units. This was the rationale invoked by the NRC as it was developing Regulatory Guide 1.232. And so they did provide guidance in developing these for non-light water reactors. However, Reg Guide 1.232 provides advanced reactor design criteria and class-specific design criteria for sodium fast reactors and modular high-temperature gas reactors, but it does not provide them for molten salt reactors. We are attempting to provide that type of information in this industry consensus standard. ANS 20.2 does provide design criteria that embody the safety objective of each of the GDCs. Each GDC was sequentially evaluated for applicability to MSRs. The GDC was directly adopted when fully relevant, things like quality assurance. The ARDC was adopted in cases where it provides a better match to MSR characteristics. And then the SFR MHDGR design criteria were adopted where they more closely match MSR characteristics. We only generated new information where we needed to. We wanted to stick with what was already an acceptable practice. The additional criteria reflective of the distinctive characteristics MSR were added to this. For example, we added a criteria to address the safety issue of activating the coolant because when the coolant flows into the heat exchanger, the delayed neutrons from there can, it's within a neutron field, and you can get activation of that. So, but one of the values we have is much like Regulatory Guide 1.232, each MSR design criteria provides the rationale for the adoption of the GDC. For example, in one of these it says derived from the ARDC. The term coolant boundary has been relabeled fuel salt boundary to reflect the difference between MSRs and other advanced reactors. So much of this is just fairly simple, but is trying to be helpful to the reviewer or the designer. The risk-informed MSR design process section introduces MSR-specific considerations into probabilistic risk formulation. So really describes considerations for implementing the risk-informed methods that have been endorsed by the NRC in Regulatory Guide 1.233. Provides MSR-specific information useful for developing a PRA following the ANS ASME RAS 1.4. Probabilistic standard for advanced non-LWR power plants. We're based upon associating, what it starts with is based on associating systems and phenomena for achieving fundamental safety functions and potential failure modes. Discusses MSR characteristics useful for performing reliability assessments. For example, passive heat transfer systems tend to be larger than active systems, which can impact safety performance during external events. And it recognizes that much of the implementation of a risk-specific, risk-informed design process is independent of the reactor class. The 10 CFR Part 53 may substantially change the preferred MSR safety adequacy evaluation method. We elected to proceed forward in the current state, unlike when Reg Guide 1.232 and Reg Guide 1.233 were developed. We paused. We said, no, people are going forward now. We need to provide a standard now, which would be useful today. And we will follow the update process that is going on for every standard. So again, we have an acceptable current process for risk-informing MSR designs and safety evaluations. Acceptable nuclear power plant safety adequacy methods continue to evolve rapidly, where the rate of change is more rapid than has been the case for the past several decades. And there are substantial changes to the acceptable methods for risk-informing designs in the draft of 10 CFR Part 53 language over the past few months. Just what was presented in August or early September is very different than what I saw in April and June. And we are trying to be an acceptable current method. We still will need to update this as all ANS standards need to be updated to be reflective of the language in Part 53 as additional methods are approved. And we'll just continue to do that. So this is going to be a living document, and the updates will be reflective of the amount of change that occurs in the next 5 years.
I believe this question was answered for the IAEA standards, but for ANS 20.2, is this for power reactors, or can it be used for research and other reactors?
Well, you don't really have the same types of design criteria for there. The NRC has adopted a version of New Reg 1537 for non-power reactors, which is reflective of their reduced potential safety, and the regulation under Atomic Energy Act Section 104, which involves what are the minimum required amount of licensing. So they have things like a maximum hypothetical accident-based accident evaluation process on there. So yes, this would provide safety insights that would be useful for that. But in terms of a regulatory process, I think you would really want to follow the 1537 type process for non-power reactors.
Yeah. And it's worth mentioning that 1537 still has design criteria in it. So you do still need design criteria for a research reactor, but maybe not to the same extent as a power reactor. It's up for ballot. What's the next step then after that? When do you expect it to become a full standard?
I have not really looked at the comments, however, and that's going to be one of my next things. However, we are supportive of both a risk-based or it could be risk-informed and a more traditional deterministic process. I have seen some parts of the comments that are not, that individuals are not as supportive of continuing to support a traditional process. But I think the working group will, as a whole, was fairly firm in its opinions. And I think we're going to have a pretty uniform set of responses to there, which would mean that we're going to be able to respond to the comments pretty rapidly and pretty determined. This is what I think we're going to get very strong votes from the working group. However, that is as a consensus standard. Other standards have taken years to resolve comments. I'm hoping that is not the case for us and that we will be able to have an acceptable standard, which then has to go through the consensus process and then the ANSI, American National Standards process, which still takes time. So maybe a year from now.
So what do you see as being the most significant licensing challenge for fuel salt preparation and transportation?
Preparation on fuel salt, but one of the things is, how are you going to do this? Are we going to prepare everything except the fissile material and then add the fissile material on site? In which case, it's going to be normal chemical synthesis, and you're just going to have a measured of this is what the composition is, this is what the purity level is, and then you'll have a Part 70 license for what's your fuel salt concentrate. On the other hand, if you're preparing the entire thing and loading the reactor core on there, you're going to need to have a manufacturing license or on this, and a fuel salt quality assurance plan on this, which is going to get, it's going to be a Part 70 license for having possession of the material. You'll need a security plan. You'll need safeguard, the full realm of things. And so you can't say any one thing in particular. I certainly think we do not have a set of standards to enable commerce yet in molten salts, because it is very difficult for saying this is the established methods for measuring what the composition and physical properties of things are in a manner which would, if you purchase it from someone, that they would have a consensus, was this acceptable?
Is this standard applicable for first-of-a-kind reactors? If you were to use it for research reactors, is there anything that would be different?
Research reactors are regulated under a different part of the Atomic Energy Act, provided they don't generate power on there. And so there is a lower level of rigor reflecting essentially the smaller source term and the smaller potential hazard to the environment. If you can show adequately small hazard, that's realistically what licensing safety adequacy is about. And that's one of those things which is really good about molten salt reactors is, while, yeah, you can spill salt, going ahead and releasing large quantities of radionuclides to the environment, we hopefully is going to be very difficult to do. And so why a number of us are in the field is we think these have some very good safety characteristics. And so yes, you need added rigor, because I don't, and you do not, you need to provide adequate evidence that you are not going to release large quantities of radionuclides or violate any of the other things about common defense, which is security, proliferation resistance, all the other elements of required licensing.
What's the relationship between principal design criteria and fundamental safety functions?
This is old versus new. in some ways. In the late 1960s, early 1970s, there was a great deal of what would constitute an adequately safe design. And if you go look at all the hearings that were developed for the atomic energy, essentially before the AEC and the Joint Committee on Atomic Energy, there was a lot of foment, and eventually the set of principal design criteria, which represent adequate safety, after about 5 years of very public effort, came out, and these are an acceptable set of principal design criteria which represent an acceptable risk. And they're good engineering practice. They seem to be very well thought out, and they've been fairly highly scrutinized. There have been some additional things that have been added to there about things like anticipated transients without scrams and the like over time. But they do represent the basic elements that if you have established these principal design criteria, that represents adequate safety. The fundamental safety functions sort of come at things from a different manner. They look at the high level of what is really important. Both of these mechanisms are supposed to achieve the same thing, which is basic adequate safety. And so if you can show you can achieve the fundamental safety function, you would have any reasonable principal design criteria also achieve those on there. So they're both supportive, and they're both trying to achieve the same thing, but they're two different ways of looking at things.
They're both, trying to achieve for the same thing. They come at it from different directions. One's kind of, inductive, and the other one's kind of deductive. You can either follow a prescription or a recipe, do these things, and therefore it's safe, or you can do the legwork and show for yourself, for your design, that you meet those fundamental safety functions. Definitely see the relationships there. That's a good question.